Hello again. We're going to continue with viewing symbolic testing techniques. Last class, I told you about symbolic testing, then we moved on and looked at the disadvantages of symbolic testing. One of the biggest disadvantages is solving the path constraint. If I collect a set of path constraints, I may not be able to solve it because satisfiability problem is in general undecidable. The current day solvers that solve these path constraints can handle linear path constraints very well. But let's say if you had something like x squared greater than 0 or log squared x greater than 0, which we could encounter while writing code, then the solutions to these become difficult. As a solution, we presented a hybrid symbolic testing technique called concolic testing, concolic as short form for concrete plus symbolic. And as I told you, it does both concrete and symbolic execution together. So today, what I'm going to tell you is one particular concolic testing tool called DART, stands for Directed Automated Random Testing. We'll look at this algorithm that DART deploys to do test case generation using symbolic testing in detail. We'll do it over 3 lectures. In this lecture, I'll introduce you to DART. We'll get started on what exactly DART does, and we'll look at a mix of concrete and symbolic execution in DART. In the next lecture, I'll walk you through the precise algorithm that DART deploys to instrument a program and to write the test driver. In the last lecture on DART, which will be the 3rd lecture from now, we will look at an example C program where a tool like DART can be applied to do concolic testing. So what is DART? DART is basically a testing technique or an algorithm that applies to unit testing phase. Let's say you have a fairly large piece of code and you are the developer or the programmer and you've been asked to unit test the code. We've seen several testing techniques to do unit test the code, but let's say you are unable to generate graph models or logic models and you have a fairly large piece of code, let's say a few 100,000 lines of code with you to test. Typically, as a unit tester, the burden will be on you to write the test driver, to instrument the program, for which there may or may not be time left. So typically, unit testers resort to what is called random testing, which is they generate a randomly generated test vector, a few of them, run the program on it. If they are lucky, they might find an error, but if they are not lucky, then they may not find an error. So what we will see today is a tool called DART, which will let you do unit testing in a reasonably automatic way. Don't have to write drivers, don't have to instrument the program yourself. DART will do it all on its own. We will see DART as it applies for C, but these days DART-like tools are available for Java, for .NET and for several other frameworks, as I told you. So what does DART do? DART follows concolic testing, which means it does both symbolic execution and concrete execution. And the advantage of DART is that it can be used to explore all feasible program paths, which means it can be done to do what is called exploratory all combinations paths testing. We've seen when we did graph-based testing that all complete path coverage is infeasible several times. So DART also may not be able to achieve complete path coverage, but it will do so whenever it can, and we will see when it can and when it cannot. So what does DART do? DART uses basically 3 main techniques to do its directed automated random testing. So what are the 3 techniques that DART uses? DART, as I told you, you just give it an executable program. DART will write the driver for you, instrument the program, run it, and tell you whether it has found an error, explode all paths, or it's unable to do either of these. It will do all these automatically. So to do all this automatically, DART uses 3 techniques to automate unit testing. The first that it does is that it extracts the interface of a program with its external environment automatically. What do we mean by extracting an interface of a program with its external environment? A program might take inputs from the user. Program might send outputs to the console. Program might read data from a database. So all these things which the program talks to or interfaces with are called external interfaces. DART first does static source code parsing and automatically extracts these interfaces of a program. And then what DART does is it writes the test driver. What is a test driver? If you remember from our lessons on integration testing, it's a program that takes and executes your main program under test. Dart generates the test driver automatically for this interface, which is basically the interface that executes the program, supplies it inputs. And what is the main job of the test driver generated by Dart? It's to randomly test a program. Randomly test a program means to give random inputs to the program in test. We will see what it means very soon. And finally, what does Dart do? Dart dynamically analyzes how the program behaves under this random testing that was done to start with in step 2. And then by systematically manipulating the behavior of the program under the random test, Dart will generate new inputs to direct the program for specific program paths. So let me repeat the 3 steps of Dart. The first step is Dart figures out automatically what are the interfaces the program has. After it does that, Dart writes a test driver again automatically that picks up a random test case from the interface and starts executing the program on the random test case. As the program executes the random test case, Dart collects a few pieces of information. Using that pieces of information, Dart will now generate newer and newer inputs that will systematically explore the program on paths around the paths that the program took on the random test case. So before we move on and understand Dart, what are the strengths of Dart? Because Dart does this interface extraction and driver writing automatically, the user or the tester doesn't have to write the test driver and the harness code to simulate the external environment of a software application. And because of that, testing can be done completely automatically on any program that compiles. We will do it for C through an example. And Dart can detect several standard errors like program crashes that happen because of errors like division by 0, violations of assertions, presence of non-terminating loops, and so on. So before we understand Dart, let me revisit the example that I had presented to you towards the end of last lecture. Here is a function h. H takes 2 arguments, integer arguments x and y, and returns an integer. It has 2 if statements inside it. First one says if x is not equal to y, you go to the second if statement. Second if statement calls a function f. Function f code is given here above. Function f basically takes an argument x and returns 2x. So it says if f of x is equal to x plus 10, which means if 2x is equal to x plus 10, then read it as that this program for h has reached an error state. So there is a word called abort and it returns 0. So now let's say this is written by a particular developer and his or her job is to unit test this code. So typically developer will resort to random testing. Let's assume that because the code is fairly large. In this case, obviously it's not a large example, but let's say assume that the developer has a large code, he or she will resort to random testing. Random testing means what? Generate random values of inputs for x and y. Let's say you generate some value, x is 25, y is 35, something like that. Now, where is the error in the program? The error in the program is here, nested inside the 2 if statements. The conditions for both the ifs should pass for me to be able to reach the error. Using a randomly generated input with high probability, I will definitely pass the first if condition. It's unlikely that the 2 randomly generated inputs x and y will turn out to be the same. So they will most likely be different. So I'll pass the first if condition. But the second if condition is very specific. It says if f of x, which is 2x, is x plus 10, then the second if condition passes. It's not very likely that a randomly generated input will pass the second condition. So no matter how many times you randomly generate an input and test a program, you might not hit the error statement which is present here in the program. We will see how Dart will, through one random generation of test case, will systematically hit the error statement in the program. So as I told you, this example program illustrates a typical problem with random testing. The function h is considered to be defective because it leads to an error for some input values of x and y. In particular, x should not be equal to y and f of x should be equal to x plus 10. That's when the input hits an error. Running a program with random values for x and y is highly unlikely to find the error because the inner if condition is highly unlikely to evaluate true for random values of x and y. So how will Dart now find the error? What are the 3 steps of Dart? Figure out the interface of the program, generate a random input to the program, run the program on it, collect some details, then systematically manipulate the details that you've corrected to direct the program on specific program paths. So Dart will begin by generating a random value. Let's say it guesses 354 for X and some 34,567 for Y, some values. Now what will happen then in this code? It will obviously pass the first if statement because X is not equal to Y, it will go. It will fail the second if statement because 2X is not equal to Y plus 10. So Dart will say that the first if statement is passed, the then branch of the second if statement was not taken, so the error is not encountered. This is a normal execution. Intertwined with normal execution, Dart also does extra bookkeeping. One of the bookkeeping that it does is to collect the predicates that evaluated to true and the predicates that evaluated to false. For this randomly generated test input, the first predicate X not equal to Y evaluated to true. So Dart remembers this. It doesn't remember it as X not equal to Y. It remembers it as X not equal to Y naught. What is this X naught and what is this Y naught? They are symbolic inputs representing X and Y. And then the second path constraint is 2X naught, which is actually going to the function f. F says compute 2x, so you substitute it back here. X is symbolically represented by x naught, so you get 2x naught is the same as x naught plus 10. As I told you, x naught and y naught are symbolic variables that represent the value of the memory locations corresponding to the values of the variables x and y. So this will give you a clue of what symbolic representation is. To represent x symbolically, give a name to the memory location of x. To represent y symbolically, give a name to the memory location of y. In this case, we have given symbolic value for x as x naught, symbolic value for y as y naught. Now, another thing to note is that how did this path expression come? If you go back to the code, this path expression came from this if condition. This if condition actually had f of x. That means that Dart had to go to the code corresponding to f, understand that f of x is 2 into x, substitute it back here and then say this is the constraint. So this comment here just says that. It says that the path expression 2x naught in this predicate is formed through an interprocedural dynamic tracing of symbolic expression, because from h the control gets transferred to the function f, from where you understand that it is 2x and then you substitute it back. Dart can do this automatically is what is being said. Now Dart has done one random generation of a test vector for x and y, collected these symbolic constraints. Now Dart wants to explore, so this means what? The program for this randomly generated input for x and y has taken one particular execution path. Now Dart wants to systematically explore the neighborhood of this execution path. So what it will do is it will do what is called a directed search. So what it starts with the execution of the program on the random input and calculates an input vector for next execution. How does it do? As I told you, when the program runs on the random input, Dart collects these path constraints. Right? So what it will do is that it will keep these path constraints, let's say, in a stack. The first constraint is this, the second constraint is this. This constraint passed, this constraint failed. It will keep that information. Now Dart wants to explore the neighborhood. Okay, for this randomly generated input, the second condition failed. So what it will now try to do is it will try to negate the second condition that failed, which means it will try to make the second condition pass. So it will generate a path constraint which will negate the second this thing, and it will give it to a constraint solver. The constraint solver will give input values for x and y that will satisfy the first constraint and that will satisfy the second constraint. So that's what is written here. For the example path on the random input, these were the constraints that were satisfied. X naught is not equal to y naught. Not satisfied, generated. X naught is not equal to y naught and 2x naught is not equal to x naught plus 10. Now what Dart will do is that it will take this second path predicate and negate it, which means it will get 2x naught equal to x naught plus 10. And what it will do is it will now try to give this as a path constraint to a constraint solver and ask the constraint solver to give it values for x naught and y naught that will satisfy this. constraint solver could give a value something like this. Let's say x naught is 10, y naught is something. And now it will check x naught is not equal to y naught, correct? 2x naught is x naught plus 10, both conditions pass. So which means what? Both ifs pass, the program has reached the error statement. This is how Dart goes about systematically exploring neighboring program paths. And in the process, if it reaches an error statement, it stops and says, I have found the error in the program. So that was Dart through an example. As I told you, our goal is to understand Dart in detail. So what are the pieces that we are going to understand? These are the questions that we'll try to answer in this lecture and partly in the next lecture. We'll understand how Dart defines symbolic variables for a given program. For this example, we'll understand how Dart came up with x naught, y naught, how did it do it? The second is, how does Dart define path constraints over the symbolic inputs while it executes the program on a random input? Which means what? Here it executed a program on a random input and it generated these two path constraints corresponding to the path taken by the program on the random input. How does Dart do that? This toy example didn't have much features, but my claim is Dart will work on arbitrary C programs, which means what? They could have branching, looping, they could have function calls, which we already saw in this example. They could have pointers and so on. So Dart should be able to generate these path constraints in the presence of all these entities. And the next part is, how does it flip one of the conditions in the path constraint? Flipping means how does it negate one of the conditions in the path constraints? How does it give it to a constraint solver, get a solution, and then run the program again on that solution? And how do you know that Dart is actually executing a different run? So these are the kind of questions that we will understand in detail. So for us to be able to understand in detail, we need to understand what the execution model of Dart is, which means how does Dart go about doing interface extraction, instrumentation, writing of driver? How does Dart do this? Remember one thing, Dart executes a program both concretely or normally and symbolically. While executing a program symbolically, Dart collects the symbolic path constraints and solves these constraints by using a constraint solver as a black box. For normal execution, it just records the values of the variables that were defined as the program executes. Now it has to execute both symbolically and normally. This side-by-side execution of a program demands that Dart instrument the program at the level of a RAM machine, which means what? We are going to assume that the program is actually residing on a particular architecture of a RAM and look at how the program will look like as it's residing in memory. We'll understand various bits and pieces of Dart. If you focus on the title slide, the first thing that I'm going to understand is symbolic variables. What are symbolic variables in the execution model of Dart? We'll understand the semantics of a program after that in the execution model of Dart, followed by understanding of statement labels, concrete semantics, inputs, and program execution. So these are the bits and pieces with which we will understand the execution model of Dart. We begin with symbolic variables. As I told you, what are symbolic variables? Symbolic variables are placeholders for actual values of a variable. In a program, as it runs in a real environment, which is the best entity to represent a placeholder? The best entity to represent a placeholder is the actual memory location. Let's say there are two variables as we saw in the example x and y. The symbolic representation of x is the memory location for x. The symbolic representation of y is the memory location for y. So first we need to understand how memory looks like. Let's say you have a 32-bit processor or a 64-bit processor or a 128-bit processor. Then what is memory? Memory for a 32-bit processor can be thought of as a mapping from memory addresses, call it M, to 32-bit words. What does plus denote? It denotes that the memory is updated. For example, suppose I write something like this, it means that M prime is the same as memory M, except that the memory location small m is updated with the value for V. Otherwise, all other memory locations in M prime, capital M prime, are the same as that of M. What are symbolic variables? As I told you, symbolic variables are defined by their addresses. Now, in an expression, M will denote either a memory address or a symbolic variable identified by that address depending on the context. As we move on, this will become clear. Now, what is a symbolic expression? Symbolic expression is the same as our arithmetic and logical expressions as we saw in the last lecture, but instead of working over normal variables, it works over symbolic variables. So, symbolic expressions could just be variable names, which are memory locations for us. It could be a constant, which is also another memory location. It could be an arithmetic expression. Please read this star e prime within brackets multiplication as any arithmetic expression. So it could be plus, it could be minus, it could be slash, it could be mod. For the sake of simplicity, only star is multiplied. But this is to be read and understood as a generic instantiation of any arithmetic expression. Similarly, this less than or equal to e prime should be read and understood as a generic instantiation of any relational operator which compares two expressions, two variables e and e prime. So it could be less than or equal to, greater than or equal to, not equal to, strictly less than, strictly greater than, and so on. Again, this not e prime, negation of e prime, is to be interpreted as representing one instances of a logical operator, can be substituted with any logical operator, and because we are using it for C, we also work with pointers. So star e prime, so this star is a binary star which is multiplication, this star is a unary star which refers to pointer dereferencing. So basically, symbolic expression is a lot like our arithmetic logical relational expression. Instead of working over normal variables, it works over symbolic variables. So it has constants, it has symbolic variables which are represented by memory location. It has addition, subtraction, multiplication, division, mod. It has all the relational operators, all the logical operators, and operators dealing with pointer arithmetic. We assume that expressions have no side effects. Now, the semantics of a program. Typically, when we look at a program, we understand what is the semantics of a program, what is the state of a program. A state of a program is the values of all the variables in the program plus a location counter which tells you which is the statement that the program is executing. So that is usually given in this transition system, where a state represents, as I told you, a tuple of all the values of a program and variable and a program counter. And transitions means what? One statement executes and a transition tells you how one state changes to another state, which value of a variable changes to which other value. So each execution of a program results in a path through this transition system. But please remember, because we are working with Dart and Dart needs to both concretely and symbolically execute a program, we need to define the semantics of a program at the level of a memory. Which means what? We define it similar to statement, the semantics that is given up here, but we say statements are nothing but simple machine instructions, because that's what happens at the level of a memory. So how are statement labels denoted? We take directly the instruction addresses that are available in our computer architecture and say those are the set of statement labels. So if L is the address of a statement, let's say a statement label, then N plus 1 is also an address of a statement. As I told you, Dart is meant to work on all C programs, but for the purpose of illustrating the algorithm of Dart, what the authors of the paper do is consider a restricted syntax. So what they say is that for now, simplicity, assume that program has only the following kinds of statements. It has a conditional statement called C, which is like a typical if statement. If an expression E evaluates to true, then go to a particular statement L prime, where E is a symbolic expression and L is a label of a statement. We also assume that in our restricted syntax, a program has only assignment statements, which assigns an expression to a memory address. And in addition to this, the program has a special statement called abort, which we saw in our example, and another statement called halt, which corresponds to normal program execution. All other statements that you will typically find in programming languages like while, anything else, can be expressed using these. So for simplicity, we assume that as far as understanding the execution of Dart is concerned, Dart has only the programming language like C on which Dart works has only condition statements, assignment statements, and special statements like abort and halt. And we also assume that there is a special function that is available to us. Let's call it statement at LM, which specifies what is the next statement to be executed. Now, concrete semantics of Dart, what will it do? It will directly give you the actual value that is stored in the memory location corresponding to every variable. For example, for an assignment function, this function will calculate this evaluate concrete, which evaluates the concrete semantics, will calculate using some address arithmetic the address of the left hand side where the result is to be stored. What are the inputs to Dart? Inputs to Dart are the memory locations corresponding to the variables, symbolic variables that actually correspond to the input. Input vector associates a value to each input parameters, hence defines an initial value of memory. So we assume, as I told you, for simplicity, that a program has only conditional statements and only assignment statements. So program execution will be a series of assignment statements and conditional statements written as A union C, any number of them, which is written using the regular expression star, and the program can either abnormally halt with an abort or normally halt with a halt. So read it like you would read a regular expression. There could be assignment statements, there could be conditions. Star means any combination of them, any number of them. This represents the program ending. Abort represents the program ending abnormally. Halt represents the program ending normally. So to further simplify and understand our model, we can assume without loss of generality that program execution looks like this. It has a series of assignment statements followed by a condition, followed by another series of assignment statements followed by a condition, and so on. Basically what it says is assignment statements and conditions could alternate. These alpha i's are assignment statements, they belong to A star, there could be no alpha i's, C i's are conditionals, and then the program always ends with an abort or a halt. S belongs to abort or a halt. So this is how a program execution looks like, and whenever a program executes, there's one path in the execution tree that the thing takes. So I'll stop here. In the next lecture, I'll continue with how Dart evaluates each of these expressions symbolically. Thank you.